OK, so I guess I'll start. All right. Well, thanks for coming back, and thanks to Jelani for organizing this and inviting me. This is great. So I'm going to talk today about chaining arguments in list decoding, or actually a chaining argument in list decoding. But I don't know why I did that. And this is based on some joint work with Achi Rudra from SUNY Buffalo. OK, so here's the plan for the talk. So I'm going to start out by sort of giving a very brief intro to error-correcting codes, which is a sort of application in computer science that we have not seen yet in this workshop. Then I'll sort of talk about where the randomness comes in, because this is sort of a probability-themed workshop. And then I'll say how to set up a chaining argument to solve the problem in error-correcting codes that will come up. And the point of this talk is really the chaining argument. So I'm not going to focus too much on the context or even the quantitative statement of the result that I'm proving, more on the structure of the chaining argument and how to bring these sorts of tools to bear in coding theory. So that's the outline. OK, so let's get started with a very high-level introduction to error-correcting codes. OK, so at the highest level, error-correcting codes are a tool to solve a communication problem. OK, and so here's one common setup for the problem. We have Alice and we have Bob. And there's some adversary in between them. And Alice wants to send a message to Bob. But the problem is that the adversary gets to corrupt, adversarially, some fixed constant fraction of her message, or gets to mess with it. So for example, suppose that Alice wants to send Bob a message about panda bears, and she wants to inform Bob that panda bears, well, they eat bamboo shoots and leaves. So she says eats shoots and leaves, and Bob gets the message, right? And this is fine, except now when there's adversarial corruption, even just a little bit of corruption can change the meaning of this message a lot, right? If the bad guy goes and puts in some commas, Bob gets the wrong idea, right? He thinks about maybe a panda bear who eats as in a hamburger, shoots as in a gun, and leaves as in skedaddles, which is not what Alice meant to say with eating shoots and leaves. OK, so this is terrible. We want to protect from this. And so error-correcting codes are a tool to deal with these sorts of issues. OK, so formally, an error-correcting code, which I'll denote by curly C, is a subset of fq to the n. OK, so fq is the finite field with q elements. So a code is just this subset, which I've denoted by these red dots here. And I want these dots to have some property that they're all pretty far apart. OK, let's say delta far apart. So here delta is relative Hamming distance, so the fraction of symbols on which these vectors differ. OK. And why do we want such a set? Well, it turns out Alice and Bob can use it for communication. All right, so here's Alice and here's Bob. And what they're going to do is somehow, algorithmically or otherwise, agree which of these red dots, which I'm going to call code words, correspond to which different messages they might want to send. OK, so maybe this one corresponds to the message Alice wants to send. Panda eats plants. There's this other, like, watch out, panda has a gun message. And there's a whole bunch of other panda-related messages that they might want to send. OK, and so now what do? Well, Alice will take the message that she wants to send. She'll look at the corresponding code word. And she'll take that code word, so this is a vector of length n over my finite field, and send it to Bob. But what Bob hears, of course, is a slightly corrupted version of this. Bob sees this received word w. So it's a smidge off. And now the good news for Alice and Bob is that if the amount of noise that the adversary was allowed to add, so if this distance rho is less than half the distance of the code, delta, then Bob can easily see that, oh, Alice meant to send this code word, and he knows exactly what she meant. OK, so that's a high-level overview of error-correcting codes. So we're good? OK, so there's some parameters that, just so you remember, I've just written them up here. So, and the few things there are many things we care about in error-correcting codes. A few parameters that we're going to care about in this talk are this error rate rho, so how much the bad guy gets to corrupt, and also the rate of the code, which somehow measures the redundancy that they use. So here, the rate is defined this way. It's this fraction. I guess this is confusing. The log applies to just C, and then the n is on the bottom. It's written less confusingly there. Which basically, you can think about this. This is the number of symbols, Q-array symbols, that Alice wants to send divided by the number of symbols she actually sends. So this is a number between 0 and 1. We would like it to be close to 1. That means there's very little communication overhead. But it might be close to 0. OK, so those are the two parameters that we're working with. Any questions about error-correcting codes? OK, great. So this talk is focused on a problem in error-correcting codes called list decoding. So list decoding comes up in the following sort of high noise scenario, let's say that there's a lot of noise. So this row, the amount of symbols that the adversary can corrupt, is more than delta over 2. Okay, so now a situation like this could happen. And Bob is kind of hosed, right? Like, there's no way that Bob could possibly tell which of these messages Alice meant to send if what he sees is this. Fortunately, not all is lost. We can say, oh, well, Bob might be a little confused, but he's not too confused. At least he knows it's one of these 4 messages, right? It's not going to be one of these other 3, let's say. Okay, so this is what we call list decoding. So Bob has no hope of recovering the unique message. There's way too much noise, but hopefully he can recover a short list. So slightly more formally, we say a code is row, comma, L list decodable if the number of code words that lives in any ball of radius row is at most L. So for example, this code is row, comma, 4 list decodable. No matter what ball of radius row that I plunk down on that picture, there's no more than 4 red dots that are going to land in it. This code is not very list decodable. I can find some ball with lots and lots of code words in it. Okay. So that's sort of this combinatorial view of what we're after. And it turns out, which is really cool in coding theory, that if Alice and Bob are allowed to use this notion of decoding, if Bob's allowed to return a short list instead of a unique message, they can actually get away with a lot of error. So over large alphabets, the adversary could corrupt a 1 minus epsilon fraction of the symbols, almost all the symbols. And Alice and Bob can still do pretty well, meaning that they have a constant rate code, only constant overhead in communication, and their list size is only constant. It's like 1 over epsilon. Okay, so even if almost all the symbols are corrupted, sort of up to constants, they can still basically solve this problem, which is pretty cool. Okay, so this is good news for Alice and Bob. It makes them very happy, as pictured here. But there's also lots of other applications of list decoding, for example, in complexity theory and pseudo-randomness. So I'll skip over this and sort of go towards the main driving questions of this talk. So the first question, which we might ask after seeing this introduction, is, well, where do we get such codes? What codes have this nice combinatorial setup, right? So what codes are near optimally list decodable up to this really big error rate, rho equals 1 minus epsilon? And so for the rest of the talk, rho is going to be 1 minus epsilon, by the way. So that's just fixed. So this very high error rate regime. There's another question you might be asking yourselves at this point, which is, where is the randomness here, right? This is supposed to be a workshop about chaining arguments. So far, everything is deterministic. Okay, so let me give you a very brief answer to the first question, which will explain the second question. Okay, so what codes are near optimally list decodable? So completely random codes. Plunk down all those red dots completely at random. Not hard to see that these are optimally list decodable, and I'll actually show you that in just a minute. So that's known. That's not too hard. There are other families of codes which are near optimally list decodable. So these special deterministic codes, most of which rely on these really beautiful algebraic constructions. So starting with the work of Goswami and Rudra in 2008, and we now know of a lot more. And then there's a whole bunch of codes in between. Sort of up until a few years ago, these were sort of the only families of codes that we knew: completely random codes or really structured super special codes. And what this talk is about is structured random codes. So this sort of fills in the gap in between and talks about sort of whole families of codes between. And so in this talk, I'm actually going to talk about, I'll give sort of a warm up with the completely random case, and then spend most of the time talking about the structured random case. Okay, so that's the high-level intro to error correcting codes. Yeah. A code is a subset of FQ to the n. Yep, yeah, which is a set of code words. Yep. Yeah, thanks. Any other questions? Yeah. You can. So the reason I'm not talking about that here is because that's actually an easier problem that doesn't require a chaining argument. Yeah, that is also an interesting regime, and I'll actually wave my hands at how to solve that problem with a chaining argument if you decided to do so. Yeah. Yeah. No, concatenation will give you a loss in parameters. Basically, the rate takes a hit. Yeah. Any other? Okay. And yeah, and so I'm already going. I feel like I'm speaking very fast, and I don't have that many slides. So feel free to interrupt me, especially because I know that not everyone here is a coding theorist, and there's lots of symbols. So please, like, if you lose track of notation, please interrupt me and get back on track. OK, so let's bring in the probability and talk about random codes. So like I said, this talk is about structure random codes. So the headline result of this work, which I'm actually not going to talk about, is about random Reed-Solomon codes. So I'm not going to define that, but that was one reason why we were interested in this middle regime. We wanted to know if there were any Reed-Solomon codes which were optimally list decodable. It turns out a random one is, and so in particular they exist. For this talk, I'm going to talk about random linear codes, which will require just fewer definitions and has exactly the same map. So a random linear code is defined as follows. So X is Alice's message that she wants to send. Let's say it has length K. And then I'm going to pick a random generator matrix, G. So this is a matrix with random entries from my finite field of size Q. I'll multiply X by G, and I'm going to get some longer vector C of X, which is my code word. And that's what Alice is going to send to Bob. Okay, so the code is a random k-dimensional subspace of fq to the n. And there's some tediousness of, well, what if this doesn't have full rank and whatever? Let's ignore that. Okay. Random matrices have full rank, sure, always. Okay. So a random linear code C is just going to be a random k-dimensional subspace of fq to the n. Okay. So this is much less random than a completely random code, but it's still a little bit random. And the question that we're going to be after is, are random linear codes sort of near optimally list decodable? So let me like keep track of our goals here, because they're going to change at the top. So goal. Random linear codes are, I'll just say list decodable, by which I mean near optimally list decodable. Up to rho equals 1 minus epsilon. And what does optimally mean? I'm going to want rate to be about epsilon. We'll see that in a minute. Okay, so that's the goal for the talk, rest of the talk. Okay. Can everyone read that? This is like super duper chalk. It's pretty cool. All right. Okay. So let's have a warm up with a completely random code. So once again, completely random code. I'm just going to plunk down these red dots, completely random. So there it is. All right. And so I claim that this statement, our goal here, is true with a completely random code. So if I have this error rate, rho equals 1 minus epsilon, and the rate of the code is about epsilon, then this code is rho 1 over epsilon list decodable. In practice, I want it to be big. Epsilon is small. But for now, let's look on the positive side and say this is a constant that is bounded away from 0. So it's big. Yeah, so basically, if you think about it, if there's a 1 minus epsilon fraction of corruption happening, you can never do better than epsilon in terms of the rate. Just there's sort of a basic information theoretic argument. So this would be optimal. This is as big as it could be given the amount of error. But yeah, exactly. We do want it to be big. And this is as big as it can be, even though it's a small number. Yeah, it's a really good question. OK, so let me prove this to you, or at least sketch the proof. So here's the picture, right? We want every single ball of radius rho that I plot down here to have not more than, say, a constant number, 1 over epsilon of code words in it. OK, so let me prove this for you. So this is an argument we've all are pretty used to, just sort of concentration plus union bound. So let's fix one of these balls, say with center W. So here's my ball. And then I'm going to just imagine looking at one code word that lands in it. That's a random thing, completely random, dropping it at random. So the probability that this code word lives in that ball is not very big. Turns out it's about q to the negative epsilon n. So it's small. Okay. And now I can imagine fixing any set of L+1 messages. And the bad event is the probability that they all land in this ball, right? That would be a violation of list decodability. Okay? And so by independence, the probability that they all land in this ball is this same small number to the L+1. Okay, so this is the bad event. And small to the L+1 is really, really small. In fact, it's small enough to tolerate a union bound over all possible centers W that I might choose, and also all possible sets lambda that I might choose. So there's q to the n possible centers. There's q to the k choose L+1 possible sets. Multiply this all by small and work it out. What you get is something like this. And it turns out that when you pick those parameters like I claimed, so pick the rate about epsilon and pick the list size about 1 over epsilon, then this is all really small and everything works out. Okay, so that's great. Now let's try it with this random linear code case. Okay, so once again, we still have some randomness going on, but a little bit less. Okay, so let's fix W here, all right? And turns out this probability that a single code word lives in this ball is still small, same definition of small. All right, now let's look at L plus 1 of them and say, what's the probability that all these guys land in the ball? Now the things are a little worse, right? These code words are not independent anymore, right? The randomness is here, and this is saying I'm picking like L plus 1 different x's and asking about the code words that come out. Okay, so those aren't independent. And it turns out the best kind of independence you can get is sort of logarithmic-wise independence. So the best thing you get is something like this, small to the log L, which is still small, but not quite small enough. And if you try to do a union bound, this is just going to fail miserably. You'll need a list size that's exponentially large than 1 over epsilon. Yeah? So I'm thinking that the messages are worst case. So Alice has her message that she wants to send, and she should be able to send any message she wants. Yeah. Any other questions? Yeah, so the only randomness here is in the selection of the code. Everything else, I'm just interested in this deterministic combinatorial statement about it. OK, so the question we have is, are random linear codes as list decodable as random codes? So that's this goal here, is to show that the answer is yes. And so here we have this situation where a union bound worked in the totally random case. Now we have a little more structure. Union bound fails. What do we do? Oh, first, yeah, sorry. Let me give you a quick, like, 2-second literature review of this problem before we move on. Yeah, so this question actually has been around for a while. Are random linear codes as list decodable as random codes? It was first asked by Elias in the early 90s for rho not equal to 1 minus epsilon, but sort of bounded away from 1 substantially. The question was answered by Guruswamy, Hastad, and Kaparti a few years ago. In this regime where rho is tending to 1, and we care about the dependence on this epsilon, for small fields, so the thing that Sid was asking about earlier, the question has basically been solved by works of Chogshi, Guruswamy, and Valencourt and myself a few years ago, which do use sort of ideas in this area, but you don't really need a chaining argument to do it. And then for large Q, that's what I'm going to tell you about today, which is this joint work with Ashi Rudra. Yeah. Too big, way too big. I would like 1 over epsilon. Yes, that's right. No, ideally, it should be independent of Q. Yep, that's right. Right, so random codes, I guess this is similar in spirit to the results we saw earlier about dimension reduction. Random matrices work great. Structured random matrices are a lot nicer in practice for a variety of reasons. So random linear codes have a lot more structure. One of actually the main motivations of this work was thinking about, like I said, Reed-Solomon codes, where the argument is very similar. And Reed-Solomon codes are actually sort of used in practice a lot. And this is a question that we answered there. But yeah, but it's basically like more structure, better. So another question is, why do I care about these randomized constructions when we have deterministic explicit constructions with efficient algorithms that work very well? And the best answer that I have to that is we're just sort of expanding our knowledge about the landscape of coding theory. So you're very close to a devastating question. Are there any other questions, devastating or otherwise? OK, so let's get on to the actual chaining argument, which is what this workshop is about. Right? So once again, union bound fails, have some structure, want to do better. So looks like a job for a chaining argument. So let's set that up. OK, so for the remainder of the talk, I'm just sort of going to focus in on this goal, and we're going to sort of leave most of coding theory behind and just talk about chaining. OK, so the first thing we're going to do is have to massage this problem a little bit to make it more amenable to sort of setting up a chaining argument. So we're going to pass from this definition of list decodability to a slightly stronger definition of average radius list decodability, which will just be nicer to look at for these sorts of methods. So list decodable, that's this picture here, Right? Remember, the definition of list decodable was if I have any set of L plus 1 points and any ball, at least one of those points lies outside that ball. Okay. So another way of saying that is all lists of size bigger than L have maximum distance from their center, at least rho. Okay. So a relaxation of this, or a strengthening of this, sorry, is to replace the maximum with an average. Okay, so say all lists of size greater than L have average distance from their center, at least rho. Okay, so I'm just saying instead of having one guy outside the ball, if I look at the average distance to the center, that average better be bigger than the radius of the ball. Okay, so the average is always less than the maximum. So that means that this is a stronger definition. If I can prove average radius list decodability, then I can prove list decodability. Okay, so this is what we're going to end up proving. Okay, so here's the definition. Is this clear? Okay, so now I have this nice clear picture. I'm going to make it unclear by putting some symbols. Sorry. So this is exactly the same thing, just in symbols. Right, so we say that the maximum over all possible sets of size L plus 1. I think that probably later in the talk I'm going to drop this plus 1, and I apologize for that. It looks ugly. Yeah, so the maximum over all sets of size L plus 1, and then the maximum of all possible centers W, that's this green dot, of the average agreement, or the sum of the agreements between the center and the code word. So this agreement here is just count up the number of positions on which they agree. And I want this to be small, right? I want the average distance to be large. I want the average agreement to be small. So I'm just writing it down this way. So I want this average agreement to be small. And it turns out the definition of small that we wanted was something like this. Okay, so this is our new goal. Let me write that down. New goal. Max. So one. Here's another one. Max W equals L, sum x in, or so I guess this is C, in lambda. Oh. I'm also being a little bit sloppy. Lambda is alternating between sets of code words and sets of messages. I'm sorry. Identify them in the natural way. Okay, so this is basically what we want. Sum over C in lambda. Okay. All right, clear? Okay, so that's the goal. Okay, so let's understand what this quantity is, this quantity max sum agreement, okay, for a random linear code. So here's my picture. This little rainbow matrix here is my random matrix, and the rows are different colors to indicate that they're independent from each other. The columns are also independent from each other, but for me it's going to be useful if the rows are. Okay, and I take this message and I multiply this matrix by this message, and I get a code word. So this vector here, so this is a vector of length n over fq, is what Alice sends to Bob. Okay, and I'm denoting different field elements by different colors. And now as x ranges over all possible messages, I get my whole code, all possible vectors that live in this subspace. Okay, and so now let's think about what is this quantity. So let's fix some lambda. So here's some set lambda. So it's a subset of my code of size L plus 1. And I want not all of these vectors to live in any ball. Right? And what is the maximum over W of the sum of the agreements? Well, it turns out this W, the W that maximizes this quantity is pretty easy to think about. It's just sort of the greedy worst case one. Right? So I'll look at this first symbol and I'll say there's two green things and there's two yellow things. So I should pick the W to be either a green or a yellow. Looks like I picked a yellow. In this one, I should pick the W's value to be green because the vast majority are green, and so on. Okay, so that's the W that kind of maximizes this agreement. And we can write down these agreement numbers. So W agrees with lambda in 2 places on this coordinate, on 5 places on this coordinate, on 2 places in this coordinate, and so on. Okay. And so this average agreement, this quantity here that we want to bound, well, that's equal to, in this case, 2 plus 5 plus 2 plus 3 plus 3 plus 2, which we can write with some notation as the sum of the size of lambda, which is L, times some notation that I'm introducing, the plurality sub j of lambda. Okay, so this is written down up here. But basically, this is normalized to just the fraction of the most common symbol that shows up in the jth row. So in this, I guess there are 6 items in lambda, so the plurality would be 2 over 6, 5 over 6, 2 over 6, 3 over 6, 3 over 6, and 2 over 6. Okay, so I'm adding all these up. Okay, so why have I done this? I haven't changed anything. There's no bounds here. I'm just moving symbols around. The reason I'm doing that is because these guys are independent now, right? The whole point was that the rows of that matrix was independent, so everything that's sort of happening on the row level are independent random variables. Okay, so in particular, these numbers are independent, and these pluralities are independent. Good? Yeah?
So unity of lambda is much bigger than Q, or most likely?
Yes, so that's a very good point. That will be like a hiccup in this chaining argument, exactly. So yeah, think about it as being bigger than Q to begin with. Or yes, actually, in this slide, lambda is definitely bigger than Q, because it's the size of the list. We're going to relax that in a minute. OK, so now we've sort of got this nice sum of independent random variables, and a common next step in arguments of this type is to pass to a Gaussian process. So we can use all these tools that we love from Gaussian processes. OK, so here's our new goal. Need to update goal. So our new goal is to show that this sum of pluralities is small. So, oh, and I guess stuff's random. Let's just slap an expectation in front. We also might care with high probability, but let's just think about expectation. Expected value of max, lambda equals L, sum of these pluralities should be small. And small here means like n times epsilon. OK, so new goal. All right. And how am I doing time? Great. So let's approach this in the standard way. So first, we sort of observe that if only we could switch the maximum and the expectation, things would work out fine. I'm not going to go through that. It's sort of standard arguments in coding theory that's OK. And so then the issue is to control the concentration, right? So we want to show that the expected value of the maximum of this deviation, this sum of independent centered random variables, is small. Okay, so that's the goal. All right. And now we can use sort of some standard tricks like to reduce this to reasoning about a Gaussian process. So the first trick that I'll use, which actually I think we haven't seen explicitly so far in this workshop when I was preparing the slides, I kind of figured we would, is a symmetrization and comparison argument. So basically, I'm only going to increase this quantity by a constant factor if I replace this mean zero random variable with this mean zero random variable. So I'm going to introduce some Gaussians. So these are IID standard normal random variables. That's the GJs. And then make sure that they have about the right variance. And also that they have the right sort of correlation structure. That's what's happening here. Okay, so this seems pretty believable. Okay, so I can, if you haven't seen this before, I can prove this for you offline later. Just ask me. So here's it's sort of a standard trick. Okay. And now let's condition on C until further notice. So I have some code C, which was originally my source of randomness, right? It's a random linear code. But now let's just say, OK, that's fixed. Now just care about the Gaussians. Okay, and we'll bring the randomness of C back into the argument later. Okay, so C is now fixed. And so all these like little colored matrices that I'm drawing, that's fixed. Okay, so now our goal, new goal, yay, is to bound the Gaussian mean width of this set, right? So this is the Gaussian mean width like Jelani had defined yesterday and like we've been talking about sort of for a day and a half now. Right, we want to show that this thing is small for some fixed C. And this is the Gaussian mean width of this set. So I look at the set of all vectors that are sort of created by these pluralities. Okay, so all right, this will be our last goal. I can stop updating this. We want to show that sum j equals 1 to n, Gaussian j, plurality sub j of lambda. Turns out we also want this to be something like n times epsilon. OK. So this is our goal. Now we want to bound this mean width, and so we're going to do a chaining argument. Are there any questions at this point? So is this like plurality notation clear? Because I'm just going to use it a lot. So if you haven't internalized it, I'll stare, yeah. There is a sum missing, thank you, yes. Yeah, there should be a sum here, sorry about that. Yeah. Or sum, yeah. Thanks, yeah. Any other questions, typos? Okay, great. Okay, so now let's try to control this Gaussian process. And so this will be sort of the remainder of the talk and the bulk of the technical stuff. Okay, so we want to bound this mean width. Okay, so here's our first try using Dudley's theorem. Okay, and this is the argument that will work for small alphabets. So we need to come up with some nets. Right? So a natural choice of nets, at least natural to me, sort of having played around with these arguments for a little while, is to choose nets indexed by sets that get smaller and smaller and smaller. Oh, actually, right. The first step is I'm actually going to change this equality into a less than equals. So instead of looking at just sets of size lambda, I'm going to look at all the sets of size less than lambda. This will be easier. Okay. And so a natural choice of nets might be, well, I'm going to look at all of the nets and then, or all of the sets, and then my next smaller net will be sets of size L over 2, sets of size L over 4, sets of size all the way down to sets of size 1. And when I get a set of size 1, that will be my smallest net. Okay? So that's sort of a natural choice of nets on this space. And a natural way to show that things are close to these nets, which we've already seen a couple of times, is to use sort of Maury's empirical method or something like that to basically choose a random subset of my set. So I start out with some point indexed by lambda, so some vector indexed by lambda, and I want to find a point in n sub t that is close to that point. What do? Let's just take a random subset of that and show that in expectation, that distance isn't too big, so therefore there exists a point that's close. Okay, so that's the basic idea. Make sense? Okay, so why should this work? So once again, here's my space that I want to find nets on. Here are my candidate nets. So let's imagine that I start out with some lambda that kind of looks like this. So there's only 2 field elements that show up here, red and blue, or yellow and blue. Okay. And here's my vector that's associated with lambda. So these are my pluralities. So this is 0.5 because half of the things here are yellow. All right. Okay, so now I want to say, all right, let's find a set lambda of size half the size so that these vectors stay close to each other. Right, so there's one. I picked a random subset, and these numbers all stayed pretty close. And if you think about it, the reason that these numbers all stayed pretty close is because if I have half yellows in the big set and I take a random set, then I have about half yellows probably in my subset. Okay, so and then turn off bound and we're done. So this seems pretty plausible. Okay, so that's why this should work. Here's a reason why this shouldn't work, which is, I think, getting to your question that you asked earlier. Like, what if my set actually looks like this? So I have a big alphabet. That's the whole problem. It turns out the argument I gave, the previous slide does work. That argument works all the way through for an alphabet of size 2. But if I have a bigger alphabet, then I might run into a case that looks like this. Okay, and so now what happens? Now I have this vector of pluralities, which is 1, 8, 28, 28, 28, 28, because each of these guys are different. And now I take a random subset, and it doesn't matter what random subset I choose. This is always going to go to a quarter, a quarter, a quarter, a quarter, a quarter. So instead of staying about the same, these numbers are doubling each time. And doubling each time, doubling is kind of the opposite of staying about the same. That's bad. Okay, and so this is kind of a bad case. And if you think about it, it doesn't need to be quite this extreme. I don't need to have all the symbols different in every row for this bad case to occur. Even if I have 10 yellow symbols, 10 green symbols, 10 orange symbols, 10 all of the things, then if I take a random subset, probably at least one of those groups of size 10 will be preserved, because I'm sort of taking this max. Right? So this is kind of just a bad thing that comes up with large alphabet sizes. And this is kind of the why previous arguments don't extend. Okay, so this is bad news. Our great idea to show that these pluralities are small are foiled by these types of sets. All right, and what types of sets are these? Well, we just said that these are sets that are sort of suffering from the fact that we had a big alphabet, but another way of saying that is that these are the sets where the pluralities are small. Okay, so let's take a look at this. Our great idea to show that the pluralities are small are foiled by sets where the polarities are small. So this should be fixable, right? Okay, so let's fix this. OK, so here's the fix. So the fix is to just change the chaining argument slightly. So the previous thing was sort of fitting in the framework of Dudley's inequality, and this will still fit in that framework. But I'm not going to use any like black box application of Dudley's inequality because it's just sort of easier to get in there and do it by hand. So we're going to do that. OK, so here's the solution. Basically, our nets are going to be made up of these sort of I meant to say these lambdas of different sizes, so choices of lambdas of different sizes, but along with a set of active indices. So what do I mean by that? So I'll start with this sort of cartoon here of my set lambda and this plurality vector. And then I'll be like, this guy, this row down here, this is a bad one. It has very small pluralities. Let's zero that out. OK? And now I'll repeat and do this argument that I did before. Let's take a set of half the size. Okay? And now there's another guy who's like basically has very small pluralities, one of each. Let's zero him out. Okay? And now I'll repeat. And now all of these guys are, have reasonably small pluralities. Let's zero them all out. Okay. And so what we're doing here is we're kind of constructing a chain starting with the biggest sets and going down to the smallest sets, keeping track of active indices as we go. And the guarantees we're going to have are basically that the active indices are never going to get too large, or sort of the numbers here on the active indices are never going to get too large, because at the point where they were sort of in danger of having this doubling behavior, we kind of nixed them. And then the other guarantee we're going to have is that the distances are never too big, which is, again, this cartoon that we had a few slides ago about why this should work. We're only ever applying that in the case where it actually should work. OK, so let me be a little bit more precise about this. So the guarantees we're going to get are as follows. So let's pick some set, some initial set of size L. Right? And so this is the set for which we want this goal to hold. Okay? And we're going to choose our set of active indices to be all the indices. And so my claim is that there exists some chain of getting finer and finer and finer sets, smaller and smaller and smaller sets lambda, and smaller and smaller and smaller sets of active indices, so that the following things hold. So first, that the difference between these vectors, these plurality vectors, is small. So if I look at successive increments, I get something that scales like 1 over root size of the set times this thing. And if you look at this thing, it's the thing we wanted to bound a few times ago, right, before we introduced the Gaussians that we're now conditioning on. Okay, so in this part of the argument, we've conditioned on the code, so that red thing is just some deterministic quantity. We'll bring it back later. Okay, so that's just the thing. Okay, and the other thing that we can keep track of is that the sum of these pluralities never gets too big. So in the tth step, basically every step it's only going to increase by a small fraction. And we're going to choose those numbers to be small enough that it all is less than a constant. And so at the end of the day, we'll have a guarantee that the sum is no bigger than, again, this red thing that was deterministic that will come back later. Yes, Sushant? Do I mean what? Yeah.
It's really the square root of the sum of the pluralities, not their squares?
That's correct, yeah. Oh, I see, yeah. Right, why is that? I think I need to, sorry, maybe get back to me afterwards and I'll try to reconstruct it. I think, yeah, this is what it is. I can, yeah, answer it for you later. But yeah, I see why you might think that it is the squares, and at the moment I also think it is the squares, and it is not the squares. But yeah, I'll get back to you. Yeah. Anything else? OK, so these are two claims. Finally, the claim is that these nets are small. So over all of the lambda knots we could have started with, as we sort of look at these nets, so if we look at the teeth net, so that's this all of the possible lambda sub little t's, I sub little t's that could possibly show up. The number of those is at most this c sub size L over 2 to the t squared. Okay, and the proof of this, without getting too technical, like why the squares are there, is basically as follows. Right, so for this first thing here, we want to show the increments are small. So we sort of go by 2 steps. So basically, the first thing we do is we might zero something out, but we only ever zero out the small numbers, so that's not going to make a big difference. And then the next thing we do is take this random subset, and because sort of all the pluralities we have here are big, we get this good concentration in that small tube. Okay. So that sort of handles why the increments are small when you just like hit it with enough Chernoff bounds. Why do these numbers never get too big? So basically the same reason. At the point that they would take off and start doubling, we truncate them and stop them from doing that. And finally, why are there not that many nets? Well, the number of sets of size L over 2 to the t is at most c choose L over 2 to the t, so that bounds the number of lambdas. And then you'll notice that the way, I guess I never formally defined these i's. I'm going to choose the i's to be all of the guys so that in the previous step, the number, sort of the pluralities were not, the unnormalized polarities were not bigger than some logarithmic number, like log L or something. And so how many of those are there? Well, they only depend on the size of the previous net of lambdas, and so that's where the square comes from. Okay. Okay. So does this seem plausible? Okay. So how are we going to use this? So these two things we're going to use for the chaining argument, right? So we're going to show that this quantity over all j's, starting with the first net, remember this is the quantity we wanted to bound, that was our goal, is about the same as the quantity at the end of the chaining when we stop. And then this thing is going to show that, well, when we stop, what we have is actually reasonable. Okay. So let's do those one at a time. Oh, first, yeah, so what is this quantity? Like I said, this is actually originally what we wanted to bound, and right now in the argument's deterministic. Let's just call it Q and forget about it for now. Okay, so now let's sort of actually do the chaining argument. So again, this is what we wanted to show, that the sum of the GJ, right, that this sort of starting level of the Gaussian process is about the same as the ending level. And we're going to use these two facts to do it. And so you can show that it's not too big. It's bounded by something like Q log C. So I'm actually going to do this on the board because I wanted to have all of this stuff visible at one time. And then I started making a slide with like \tiny and then a lot of equations. And I thought, oh, that's a bad idea. So let's do it on the board. Let's see. Does that help at all? Yeah, OK, cool. All right, so let's sort of just do this chaining argument. So this is the same type of argument that we've seen a bunch of times before in these past 2 days, but it's always good to see more of them. So it's just one board of a little chaining argument. OK, so right, with the thing we want to bound is this delta, which is the sum over all the j's, gj PLJ lambda t, minus what we get sort of at the end of the thing, the sum over j in the last set t. T is going to be some log L type of deal. Gj lambda t. Okay, so we'd like to bound this, and we're going to do it in terms of the increments. Oh, sorry, this is lambda naught. Lambda t minus, and this is I sub t. It's important, some j in I sub t plus 1, gj PLJ lambda t plus 1, right? And so we have this telescopic sum. Lambda is the sum of the lambda t's, or delta is the sum of the delta t's. Right. Okay. And so what this frame says is that each of these delta t's is a Gaussian random variable with variance something like root q over size of lambda t. So is q over size of lambda, delta lambda. They're both triangle shaped. Lambda t, which is roughly 2 to the t over L times q. Okay. All right, and now we're basically done, right? So now we just do this chaining argument. So what that means is that the probability that any one of these increments is big, so the probability that delta t is bigger than u, let's say, for all t. Well, let's take this union bound. Okay, so this is no bigger than the sum over t equals 1 to t times the number of things in this net we need to deal with. So how many increments are there? Just like we saw, there's over 2 to the t squared size of this first net times size of the second net. Okay, so that's sort of the possible number of steps we might have. Yeah, Jelani? Yes, I did. Thanks. Yeah. 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 Fine. The point of a blackboard is not to be more informal, right? Who cares about indices? Okay. Right, exists a t so that these guys are large. These guys were delta t. Okay. Not much bigger than this giant union bound, and then this concentration, negative u squared over variance. Right? And so if we choose u to be about the right size, we can make this all really tiny. And what u do we need to choose? Turns out let's choose u like that. So choose u about q log c, and everything is good. Okay, and then I have that basically in the favorable case, lambda t is, lambda is no more than the sums of the delta t's, each of which is no bigger than u, and so that's capital T times q log c, and I'm going to choose my capital T to be logarithmic. And my twiddles are hiding log L factors. Okay. Right, so I've already hidden a few factors of log L in the concentration argument, so here's just some more factors of log L that are hiding. Okay, so that's, there we go. Okay, so that's just sort of the basic chaining argument that we've seen before, slightly informally, but that's the basic idea. Okay, so is that good? Question? Okay, so that's the chaining part, right? So now we've sort of used these two facts, and we've gotten this conclusion. Okay, great. And so now we're basically done. So remember, the other part was to show that by the time we got to the end, we got something reasonable. So here's the guarantee we had before. And it turns out, I'm not going to do this on the board, you can do this in your head or on paper, that just these two things imply that this is reasonable, like root q or something. Okay. So those are basically the two steps. And when we put them all together, what we get is that this thing, that was our goal, is no more than root q log c with some twiddles that are hiding constants and log L factors. And plugging in what I said that definition of q was, it's this. Okay, so why did we want that again? Let's sort of trace back through these sets of goals. Okay, so we wanted that because that was bounding this Gaussian process gave us a bound on these sort of original un-Gaussianified symmetric random variables. Okay, so now we've bounded that like this with just an expectation in front of this. Oh, there should be a max over lambdas in there, sorry. Yep. Okay, so now we've bounded this in terms of that. And now these red things, these are basically all what we were trying to find in the first place. So we've seen this trick before in this workshop. Now we just sort of solve using the red things and sort of write out the quadratic equation and solve it out. And what you get is that, along with sort of using the fact that the expected value, or that the maximum of the expected value was fine, so that would be this term here. We already said that that was fine. What you get is that the expected value of the maximum of these pluralities, so we're moving up a level, that was this goal, is no more than n epsilon plus log size of c. That's what you get after chunking through the math. Okay, so that's what we just saw. And now if we compare that to this goal here, which was just to show the whole thing is on the order of n times epsilon, we see that we'd like to bound log c by something with n times epsilon. And solving that means that log base q of c over n, that's the rate of the code, definition, rate, should be about epsilon by log q. So this is not quite in line with what we wanted. We really wanted rate about epsilon going all the way back up to our first goal. That's what the random codes got with epsilon. So this is not quite right. There's this extra log q factor. And slightly more precisely, so here's the formal statement of the theorem. If we suppose q is big enough, again, if q is small, we can deal with that via other means, and we have a random linear code over fq, then we get, with this rate, so choose the code of this size, then we get, with high probability, the code is list decodable up to this error rate, 1 minus epsilon. So some bad guy can destroy a 1 minus epsilon fraction of the symbols. And Bob's confusion is not much. He only gets a constant size list out. Okay. And so here I'm bringing back in all those log factors that I suppressed. There are 5 of them. But these log factors are not nearly so worrying as this log factor. And the reason is that here q is growing. So if we could remove this factor of log q, that would be really cool. The other log factors, after we realized that probably we'd have a few, we got a little sloppy. So you could certainly do better than 5. But I'm not sure if you can get them all the way down. OK. So that's the statement of the theorem. Are there any questions? Yeah, Sid. Yeah, it's a good question. I thought a little bit about that, and I didn't see an easy way to adapt our argument to do that, but I don't see any reason why it shouldn't be true. I think it's just like our argument is kind of brittle in this way. Yeah, Clement. I really believe the q should not be there. If it were, that would also be surprising, if you could prove that it were there. But yeah, we don't know. This is the best we have. Yeah. That is a great question. I have thought about that. I cannot make this method work for that. And the reason is a little subtle, but basically it's like instead of controlling these pluralities, it turns out you want to control exactly the same sum, except if you look at the distribution that shows up in the jth row of that lambda, you want that distribution to be close to uniform. That's what it means to be a strong extractor, basically, in this sense. And somehow this argument just doesn't work with that, and I don't know. Yeah, I think that's a really good question, and I hope that there would be a way to adapt these techniques to work there. Any other comments? But yeah. Sorry, say again? I didn't hear you.
So there are some other so-called code problem, list-decoding problem, and there in non-linear code they have high degree problem.
Oh yes, yeah. And so these results do work for. So those are still linear codes, but they're defined using high degree polynomials. You mean?
I don't think that.
So like Reed-Solomon codes or Reed-Muller codes. Yeah. So this result will work for Reed-Solomon codes as well. It shows that that's high degree polynomials, high degree univariate polynomials, instead of this random linear code is basically looking at functions, linear functions. But if you look at high-degree univariate polynomials and pick random evaluation points, this result holds there as well. Okay. Yeah. Yeah, that's a good question. Actually, that setting was the motivation for this work, was the Reed-Solomon codes. I just didn't want to have to define even more stuff. Any more questions?
Where is it extracting the argument that you use in that code?
Yeah, right. So that's a really good question. So let's, yeah. So next question. What did we need from these random linear codes, right? So we needed that we had these independent symbols, so independence of the rows, and we needed that the max of the expectation was about right. And really, that's all we needed. So this result is much more general than random linear codes. So again, it applies to Reed-Solomon codes and yeah, just with random evaluation points, and also basically to anything where you have this set up. Yeah, and so this result's actually much more general. Great question. Any other questions about the result? Yeah. Yeah, so I've been using this rate epsilon, which actually the correct rate is which turns out to be about epsilon. So I was just simplifying this expression with the Q area entropy to when epsilon is small, these guys are about the same.
So you're saying actually linear
Yeah, the list decoding capacity. Yeah, exactly. Up to these log junk. Yeah, that's right. Yeah, so there's something called the list decoding capacity theorem, which bounds how well you can do in terms of entropy, and this is that. Yeah. Okay, so if there are no more questions about the same result, let me just sort of quickly wrap up. How am I on time? Okay, great. So just to recap, so we used a chaining method to talk about the list decodability of structured random codes, which kind of lay in this no man's land between the few very explicit structured constructions we have in the completely random case. And some punchlines were that random linear codes are nearly optimally list decodable. That's the result we just saw. There's this result that I've been alluding to that I haven't even defined the terms of, which is that there are Reed-Solomon codes list decodable beyond the Johnson bound. I haven't defined any of those terms, but that's sort of if you happen to know them, this is the punchline of that result. Or this is the punchline of the same technique. And more generally, like Oded was hinting at, these techniques work for anything with independent symbols and any sort of reasonable behavior when you don't have to take a union bound, when you get to switch maximum and expectation. Okay, but there are many open questions, so let me just end with those. The first is to remove all these superfluous log factors. And like I said, this log Q is especially obnoxious. And I should say, I think this is the first talk today, which has not ended. In follow-up work by Jelani, all the log factors have been removed. So yeah, hopefully someone can deal with this. And a related question is to find a simpler proof. So this, I sort of gave you a sketch here, but the actual proof gets very technical, and it's just there's like too many turn-off bounds and too many different cutoffs and too many parameters. And I think there's a very simple proof for the Q equals 2 case, and there should be some way to find a very simple proof for this large Q case, and I'd really like if someone could find that. Another question is a nice characterization of codes that are list decodable to capacity like this. So I showed you that a random one was, but actually find me one. So we know of linear codes that do, but find me a Reed-Solomon code that's list decodable to capacity. We don't know how to do that. And finally, this question that was already asked, applications to other pseudorandom objects. So in particular, I have up here, is a random linear extractor optimal? It's a very good question. Yeah. Okay, so that's all. So thanks for listening. Any more questions? Yeah.
Would it be interesting to look at any other distances than Hamming distance?
Yeah, so I mean, so people look at rank metric codes. Have you heard of these? So this is where the code words are matrices, and the distance is the rank of the difference of two matrices. So that's another metric that people care. Like people study list decoding for. People also look at codes defined over the reals or on spheres. You can look at spherical codes and stuff like that, where it's geodesic distance or things like that. But yeah, but the rank metric one in particular is something that's of extreme interest because we are very bad at proving stuff about list decodability of rank metric codes. Yeah. Any other questions? Okay, well, thanks.